Good evening, everyone. Okay, so first of all, we would like to welcome Professor Takaki Kajita and Mr. S.D. Shibulal, who are on the stage with some flowers. Vidya. Yeah, Mr. Shibulal, please. Now, no. I would like to request Mr. Shibulal, who is presiding over today's function, to welcome our eminent speaker.
Good evening, everyone. It's a great pleasure for me to be here. A very warm welcome to Nobel laureate Professor Takaaki Kajita from the Institute of Cosmic Research, Tokyo, Japan. He is also the winner of the 5th TIFR-IUPAP Homi Bhabha Award. At the outset, I want to thank Professor Kajita for taking time out of his very busy schedule to be here as a distinguished Sarojini Damodaran speaker. Professor Kajita has been awarded for his discovery in neutrino oscillations and other path-breaking contributions in the field of astrophysics. This discovery had a huge impact on our understanding of cosmology, cosmic ray, particle physics, and open doors in many other scientific fields. Professor Kajita leads KAGRA, a large cryogenic gravitational wave detector, and the next generation neutrino detector, Hyper-K, both located in Japan. Our hearty welcome to you, Professor. Physics and math has been my favorite subjects in school. I learned physics and maths for many, many years. In fact, I did my post-graduation in physics in 1977. So I feel very fortunate to be here to listen to you speak. Now, my association with TIFR started in late 70s when I was here to learn computer science. This was in 1979 to 1981. When I entered this campus in 1979, I hardly knew anything about computer science. I was a novice in the field of computer science when I came here. Everything I learned about computer science, which built my career and my life, the foundation was laid in this campus when I studied here. I had the fortune of meeting some wonderful teachers, Dr. Ramani, who was with the computer science department, Dr. Mudhur, Ms. Jogalekar. These are the teachers, the wonderful teachers whom I met in this campus. The knowledge I gained here laid the foundation for my career, my life, and later on, it allowed me to take a master's in computer science from a US university. And more importantly, I was just married in 1978, and myself and my wife, we were living in Bombay, hand to mouth. We had no money, but all the other things in life. So she used to accompany me to this campus very often. So canteen was our favorite place where we could get good food at low price. So we used to walk around this campus, enjoy the beauty of the place, the seaside and the wind. So we have very fond memories of this campus. So we are very, very glad to be back here. It brings back a lot of wonderful memories for us. With that, let me stop. I do not want to take up any more time, as I know that the audience is eager to hear Mr. Kajita speak, as I am. I want to thank the management, the faculty of TFR for making this happen. I also wanted to thank Mr. Murali, who is sitting here, Dr. Murali, who is coordinating with TFR on all these activities. Thank you very much.
Thank you, Mr. Shibulal. Once again, a very good evening to everyone and a very warm welcome to the public lecture by Professor Takaaki Kajita, which is being organized by the Tata Institute of Fundamental Research, that is TIFR. Now, the poster which you have seen of Professor Kajita's lecture is a combination of two pictures. The top one is of Grapes 3 experiment of TIFR that is located 2 kilometers above sea level in Ooty. The bottom picture is of Super Kamiokande Experiment, about which you will hear from Professor Kajita, which is located 1 kilometer underground and is led, of course, by Professor Kajita. And Grapes 3, actually, why I mentioned is not just because I'm part of it, it is also a very strong India-Japan collaboration where a large number of Japanese scientists have been participating side by side their Indian counterparts for past 25 years. Moving on, may I request all of you to kindly either switch off or put your mobile phones in silent mode. In keeping with the traditions of this institute, we would first proceed with a vote of thanks so as not to interrupt the flow of public lecture by Professor Kajita and your subsequent interaction with him. I would like to take this opportunity to express our sincerest gratitude to Mr. S.D. Shibulal, one of the founders and former CEO of iconic Infosys, for agreeing to preside over this event and supporting it through Sarojini Damodaran Foundation. We are extremely happy that Mrs. Kumari Shibulal, their son Shreyas, and very soon their daughter Shruti will also be joining to listen to this lecture, and a warm welcome to all of them. We would like to thank Professor Sandeep Trivedi, the director, TIFR, for various approvals. Professor Trivedi had expressed his sincere regrets for his absence due to some family commitments. We would next like to thank the staff of the Public Relations Office, the auditorium, the technical services, the transport services, the security, the canteen, the cosmetic maintenance, the account section, the outreach committee, the computer section, and all other administrative wings of TIFR for their active and willing help in organizing this event. I would especially like to acknowledge colleagues who have shouldered numerous organizational responsibilities connected with this event with an enthusiasm well beyond anything that I could have asked for. Special thanks must go to Venkatesham Reddy, Pranabal Nayak, Santosh Chavan, Sam Morris, as well as several other members of our department. They have worked tirelessly for the past several days on various responsibilities to make this event successful. And finally, we are truly grateful to all of you for having set aside your evening to come and listen to the wonderful lecture that will shortly follow. So before I introduce Professor Kajita, let me introduce myself, because nobody knows me, everybody knows him. So my name is Sunil Gupta, and I have the privilege and honor of introducing today's speaker. Of course, as I said, Professor Kajita really doesn't need any introduction, but nevertheless, let me proceed with a brief formal introduction. So during his PhD in the early 1980s, Professor Kajita was studying the intensity of atmospheric neutrinos. Now, right now, don't worry about what neutrinos are, because he will tell you very shortly what they are, to verify the existing theory. He discovered that the ratio of atmospheric muon neutrinos and electron neutrinos in his experiment, which was known as the Kamiokande Experiment in Japan, could not be explained on the basis of physics of that era. So this was very interesting. So he found something which could not be understood. Now, it is anomalies like this that have historically proven to be fertile ground for new scientific discovery. That's what we know. Every time something new happens is because something is not understood. However, the history of science also shows that great discoveries are made when new and more sensitive instruments are developed by teams of experimental scientists and engineers. That's what Professor Kajita did by playing a critical role in the development of large photomultiplier tubes and in development of water Cherenkov detectors with a team of exceptional colleagues. And he developed what later on came to be known as Cherenkov rim imaging technique, which could detect electrons that are produced by decaying muons in his detector. This development led to the first important experimental indication of neutrino oscillations from the atmospheric sources in this Kamiokande detector. Now, I said it's a water detector, so the question is just how much water did he use in the Kamiokande detector? Well, that water was enough. If you pour that water into this hall, it will fill it up from floor to ceiling. That's how much water he used in that detector. So it was massive detector. Okay. He subsequently led the team, his team of scientists, to build the next generation of super Kamiokande detector, or Super K. It is now known as Super K detector, that announced the evidence of oscillation of atmospheric neutrinos in 1998. And the next obvious question is, how big was Super K? So Super K was almost 10 times bigger. So you could fill up 10 Homi Bhabha auditoriums with water. That much water it had. Okay. He studied the direction of atmospheric neutrinos, not just he detected them, and established that there were missing neutrinos, and thereby proved the existence of neutrino oscillations. Neutrino oscillations were an unexpected and possibly the greatest discovery of past half century, as evidenced by the award of Nobel Prize to Professor Kajita in 2015. This discovery had a huge impact in science. The consequences of that are still being felt. But Professor Kajita is not someone who would rest on his laurels. And he currently leads, as Mr. Shibulal mentioned, the KAGRA experiment, which is the Kamiokande gravitational wave detector, uses cryogenic technology. And he also leads the next generation of water Cherenkov detector, which is called Hyper Kamiokande, or Hyper K. And Hyper K, now you can guess, it is 10 times bigger than Super K, or 100 times bigger than Kamiokande, so you can fill up 100 auditoriums. Maybe a stadium you can fill up with water. That's how huge it is. It will take him nearly a decade to build that experiment. And of course, it will need a large team of scientists and engineers to do that. Professor Kajita is a recipient of a large number of honors and awards by various scientific bodies across the world. Since I do not have the time to list them all, I would just like to mention one that he won in 2016, and that was the Breakthrough Prize. He also has myriad other responsibilities. He is co-chairman of the multidisciplinary International Neutrino Panel created by the International Union of Pure and Applied Physics, IUPAP, which is tasked with the responsibility to design the next generation of neutrino experiments. He is an adjunct member of IUPAP Commission C4 on Astroparticle Physics. He is also the director of Institute for Cosmic Ray Research and a professor at University of Tokyo. Now I would like you to travel back about a decade. In 2010, TIFR, in association with IUPAP, had established a prestigious international award in the field of cosmic rays named the Homi Bhabha Medal and Prize. This was done to commemorate the centenary of the birth of Dr. Bhabha, who was not only the founder of TIFR, but also of Atomic Energy Program and a force for starting the space program in India. No wonder that in view of his path-breaking contributions in advancing our understanding of cosmic radiation through discovery of neutrino oscillations, Professor Kajita won the TIFR-IUPAP Homi Bhabha Award in 2019. Today's public lecture is being delivered by Professor Kajita in his capacity as the winner of Bhabha Award and as a Sarojini Damodaran Distinguished Visitor. Before I call upon Professor Kajita to deliver his lecture, I'm very happy to announce, and I know that most of you will be very happy to hear that Professor Kajita has agreed to answer your questions at the end of his lecture on the fascinating topic of atmospheric neutrino oscillations, the first evidence of new physics. Immediately after the conclusion of the question-answer session, tea and snacks will be served just outside the auditorium. So, thank you, and Takaki, please.
Oh, thank you. Yes, okay, thank you. Yeah. Good evening. Well, first of all, I'm very glad to be here at Tata Institute of Fundamental Research. The reason is, well, I knew Tata Institute for almost 40 years because Tata Institute was a very important institute for the cosmic ray physics and in particular the underground physics, which I'm going to discuss today. And well, I'm honored to be able to give a Homi Bhabha lecture. So this evening, I want to talk about atmospheric neutrino oscillations. By the way, here in this slide, you see a photo. And this is the super Kamiokande detector. And I have been working with this detector for more than 20 years. And therefore, today, I'm going to discuss our work with this detector. And this is the outline of this talk. First, I have a brief introduction of neutrinos. Then I want to move on to the research career. Then discovery of neutrino oscillations. Also, I want to briefly discuss the discovery of solar neutrino oscillations. Then before finishing, I want to talk about the reason why physicists are excited with the small neutrino mass. Then I'll summarize this talk. Okay, now this introduction. What are neutrinos? Okay, so here is the summary of neutrinos. And neutrinos are fundamental particles like electrons and quarks. But you may ask, what are the differences between the neutrinos and other particles? And well, my answer is neutrinos are something like electrons without electric charge. In fact, the part without electric charge is very important. Because of this nature, neutrinos can easily pass through even the Earth. But fortunately, they can interact with matter very rarely Therefore, we are able to study neutrinos, although it's not easy to study them. Now, also I want to inform you that neutrinos have, like the other particles, 3 types, namely electron neutrinos, muon neutrinos, and tau neutrinos. And finally, I have to tell that neutrinos have been assumed to have no mass. Okay, excuse me. Okay, okay, so this is almost all about neutrinos. Then you may ask, how can we detect neutrinos? Well, first of all, we can never see neutrinos themselves. Then, how can we study neutrinos? Well, of course, in almost all cases, neutrinos pass through even the Earth. However, sometimes neutrinos interact with the nucleus. Then a charged particle is emitted in many cases. And if a charged particle is emitted, then we have many ways to observe these charged particles. And in fact, in our experiment, we use this method. As introduced, our detector has a lot of water, and therefore a neutrino interaction occurs in the water. Then charged particles propagate in the water. Then photons are emitted. Now, since photons are emitted, so you can easily, well, actually not so easy, but you can observe these photons or light. So in our case, we have the photodetectors on the detector wall, and we observe these photons or light. And this way, we observe the light pattern, and by analyzing these light patterns, we know neutrino interactions occurred at this moment. So this way, we study neutrinos. Today, I'm going to discuss neutrinos created in the atmosphere of the Earth. These neutrinos are called atmospheric neutrinos. And here in this slide, I'd like to briefly explain how these neutrinos are created. Well, from somewhere in the universe, cosmic ray particles are arriving to the Earth. And these cosmic ray particles enter into the atmosphere, they interact with air nucleus. Oh, by the way, I think I should mention, explain a little bit about cosmic rays. Cosmic rays are high-energy particles. Many of them are high-energy protons, but sometimes helium nuclei, or even sometimes iron nuclei are coming to the Earth. These are the cosmic rays, and these cosmic rays interact with the air nucleus, and then typically pions are produced. Pion is one of the elementary particles, and this pion is unstable. Then this particle decays to a muon, then to electron, and during this decay chain, neutrinos are created. These are called atmospheric neutrinos because these neutrinos are created in the atmosphere of the Earth. Oh, by the way, well, I said these cosmic ray particles come from somewhere in the universe. In fact, we still do not understand how these cosmic ray particles are created in the universe and where these particles are created. Therefore, there are many, many scientific studies of cosmic ray particles. In fact, my institute is, of course, Institute for Cosmic Ray Research. Therefore, my institute is studying cosmic rays. And in fact, there are many cosmic ray studies or many cosmic ray experiments. And one important experiment is GRAPE-3 in India. And actually, well, this was also mentioned, and which is an India-Japan collaboration. So, well, this fact tells us that India and Japan are working together in cosmic ray studies. Now, if neutrinos are created in the atmosphere, then, of course, we'd like to study or observe these atmospheric neutrinos. In fact, the discovery of atmospheric neutrinos was made more than half a century ago. In 1965, atmospheric neutrinos were observed for the first time by detectors located very deep in underground. In fact, there were two experiments. One was this experiment. This experiment was in India. And again, I want to say, this experiment was carried out by scientists from India, Japan, and the UK. And another experiment, shown here, was located in South Africa. Both of these experiments were located extremely deep underground, and these experiments observed atmospheric neutrinos for the first time. And, well, today I'm going to discuss atmospheric neutrinos in my talk. Okay, now I want to move on to my studies. Well, I said today I'm going to talk about neutrino studies, but the motivation was slightly different. Let me tell you, in the 1970s, new theories of elementary particles predicted that protons should decay with the lifetime of about 10 to 30 years. Of course, 10 to 30 years is a very long lifetime. In fact, well, even if proton decays or not, we don't care in our daily life. But this prediction was scientifically extremely important. Therefore, several proton decay experiments began in the early 80s, and this is a list of the experiments that started the search for proton decays in the 80s. The first one was the KGF experiment in India. And again, I want to mention this was an India-Japan collaboration. The second one was NUSEX in Europe. The third one, IMB in United States. Fourth one, Kamiokande in Japan. And the fifth one, Frejus in Europe. So from now on, I'm going to discuss this Kamiokande experiment. Okay, this is the sketch of the Kamiokande experiment. It was a large water detector It had about 60 meters in diameter and 60 meters in height, and it contained about 3,000 tons of very clean water. And if a proton in the water inside this tank decays with the lifetime of about 10 to 30 years, then in the moment a proton decays, several particles are emitted. And these particles emit light or photons, and therefore we installed photodetectors onto the inner surface of the detector. So this was the Kamiokande, and this was located 1,000 meters from the surface of the mountain. By the way, I believe most of you do not know the location of the Kamiokande experiment. Well, okay, so the location is there, here. So you notice that the experiment was in the mountainside of Japan. In fact, you are right. The site looked like this. In fact, this photo was taken in the early 80s. So, well, indeed, the site looked like this. And you notice several facilities there. And these are the facilities for the mining activities. So the Kamiokande experiment was constructed in an active mine. And in fact, the detector was located inside this mountain. Well, of course, you cannot buy these detectors. Therefore, you have to construct these detectors. So this was the team of scientists who worked for the construction of the detector. And, well, you can see Professor Koshiba in front, in the middle, in front in the center. And he was my thesis advisor. And in fact, he was the Nobel laureate who received the Nobel Prize in 2002 based on the neutrino study with the Kamiokande experiment. By the way, well, you notice all of us wear helmets and rubber boots and the working clothes. So this was the style for us to go into the experimental site. Of course, it was natural because our experiment was located in an active mine. Anyway, every morning from the mine entrance, we went into the construction site. And then the construction work was something like this. Well, I said the Kamiokande detector was 60 meters high, and we had to install the photodetectors onto the detector wall. So we had a problem. 16 meters is really high. Therefore, we had to find a good way to install the photodetectors onto the detector wall. Of course, we had several discussions, several ideas, and finally, we decided to use these plastic boards to install the photodetectors. Well, if we finish installing the photodetectors, then we raise the water level by 1 meter and then begin to install in the upper level. This way, we installed the photodetectors. In fact, we were successful. No one dropped from the boat. Anyway, the experiment began in July 1983, and we were hoping that we should be able to observe proton decays maybe every week or maybe every month. But unfortunately, the proton lifetime was much longer than theoretically expected. So we didn't find any proton decays. Instead, we observed background events. They are the interactions of atmospheric neutrinos. So after 3 years, we still had no evidence for proton decays, but we had accumulated many atmospheric neutrino background events. Therefore, at that moment, we thought that we have to improve proton decay analysis in order to better separate the proton decay signal and the neutrino background. So we developed new software to improve the proton decay analysis. Well, of course, if you have a new software, you have to test this software extensively. Initially, this software contains a lot of bugs. So this software never ran properly. So we have to check this software very extensively. And indeed, we did various tests. And as a final test, we studied the neutrino type, namely electron neutrino or muon neutrino interactions. Then we found that the number of muon neutrino events was much fewer than expected. This was the typical muon neutrino interaction event. And we found these types of events were much fewer than expected. Well, at that moment, as I said, we were testing the new software. And the result was something unexpected. And that means the software must be wrong somewhere. So we thought that it's likely, very likely, that there was some mistake somewhere in the software. Therefore, we have to find out the mistake. So we started various studies to find out mistakes in the late 1986. Well, that was more than 30 years ago. And I think around that time, we had a lot of time. And in fact, we tried to find that mistake for about a year. But even after 1 year, we didn't find any serious mistake. So we concluded that the muon neutrino deficit cannot be due to any major problem in the data analysis nor the simulation. Therefore, we decided to write a paper because we had a high confidence that we observed something unexpected. Then it's our duty to report this kind of data to the scientific community. So we wrote a paper, and the paper itself was quite simple. Okay, there's something strange, but let me explain. Well, we simply counted the number of muon neutrino events observed in Kamiokande. That was 85. and then compared with the expected number of events based on the simulation. The number of expectation was approximately 144. Clearly, there was a big deficit of data events. And we did the same comparison for the electron-neutrino events. And for electron-neutrino events, the data and simulation agreed reasonably well. So we simply reported these numbers. Well, okay, we had a very careful check for more than a year, and we had high confidence that the data are correct. But the response of the scientific community was rather negative. People were discussing there must be something wrong in the Kamiokande analysis or something like that. But, well, as I said, we tried to find out mistakes in about a year, for about a year. So we thought that the data must be right. And, well, to be honest, we had no clear idea what was the cause of the deficit. But we felt that we are facing something very important. So I was most excited with the data, and therefore I changed my research from proton decay analysis to neutrino studies. And in fact, I enjoyed to find out the cause of the deficit. But unfortunately, during the Kamiokande time, we were unable to find out the clear reason for the deficit. Anyway, well, I have been doing scientific studies for almost 40 years, but I want to say around that time was most exciting to me. Clearly, I had a feeling that we are facing something new, something unknown. And really, I wanted to find out what was the cause of the data that was the deficit. Well, okay. I said we didn't have any clear idea what was the cause of the deficit. But from the beginning, we have been thinking that maybe the deficit of atom-shaped muon neutrino is due to neutrino oscillations. Well, okay, well, I mentioned neutrino oscillations without any explanation about neutrino oscillations. So here in this slide, I want to explain what are neutrino oscillations. Actually, neutrino oscillations were predicted more than half a century ago by theoretical physicists. They were Maki, Nakagawa, Sakata, and Pontecorvo. And these people predicted if neutrinos have mass, these neutrinos change their type from one type to the other. For example, a muon neutrino may change to the type to a tau neutrino. For example, oh, I'm sorry, this tau neutrino should be over there. If a muon neutrino is created at this point and begin to propagate to the right, then at some point, this muon neutrino changes to tau neutrino. But if they still propagate further, then the neutrino type come back to muon neutrino. Then at this point, tau neutrino again. So this way, neutrino type changes. And this is neutrino oscillation. And if neutrino oscillation is in fact occurring, then we can easily explain the muon neutrino deficit. However, of course, there could be several other possibilities to explain the muon neutrino deficit. Therefore, we wanted to have the data that could separate the neutrino oscillation and other possible explanations. And for this, we thought this way. Well, I said these neutrinos are created in the atmosphere of the Earth. These neutrinos are created in every place in the atmosphere. And therefore, some of them are created above us, maybe 10 to 20 kilometers above us. And these neutrinos, after traveling 10 to 20 kilometers, they come to the detector. So they only travel 10 to 20 kilometers. Therefore, they may have no time to change their type. On the other hand, neutrinos are also created in the other side of the Earth. These neutrinos must travel long distance before reaching to the detector. They have to travel typically 10,000 kilometers, which is a very long distance. So these neutrinos may change their type while propagating in the Earth. So if we think this way, we naively expect we should observe the up versus down asymmetry of the atomic muon neutrinos if the deficit is due to neutrino oscillations. Yes, of course, we wanted to observe this effect in Kamiokande. But unfortunately, Kamiokande 3,000-ton detector was too small to observe this effect. Therefore, we needed much larger detector than Kamiokande, and that was Super Kamiokande. Now, I want to move on to the discovery of neutrino oscillations. As I said, we needed much larger detector, and that is Super Kamiokande. It is, in fact, much bigger than Kamiokande. The volume that can be used for the physics study is about 20 times larger. In fact, Kamiokande has about 40 meters in diameter and 40 meters in height, and it contains 50,000 tons of very, very pure water. And it is an international collaboration. We have about 180 collaborators from 10 countries. And again, well, of course, we have to construct the detector. And well, in 1995, for almost a year, we worked to construct the detector. This photo was taken in the spring of '95 when we were installing the photodetectors on the top plane of the detector. So you see, many people worked in the detector to install the photodetectors. And well, in fact, these many people worked for about a year to construct the Super Kamiokande detector. And I also want to mention that maybe about 80% of these people are physicists, Super Kamiokande collaborators. So in 1995, Super Kamiokande collaborators came to the Kamioka mine and worked in underground for about a year. And finally, in January '96, the construction of the detector almost finished, and we began filling water into the super Kamiokande tank. And this photo was taken in January 96. And this photo was taken from the top of the detector, viewing the super Kamiokande detector inside. And in fact, we started the experiment from April 96. And we observed neutrino events like this. This is a typical muon-neutrino interaction. And we observed these neutrino interactions with the rate of approximately 10 events per day. Of course, the number of events we observe is not so many, but there are many other background events. Therefore, we need many people to find out the neutrino interactions, removing all the other backgrounds, and therefore, we formed a group of people to study these neutrino interactions. And these people worked together very extensively for about 2 years. And after 2 years, we were able to report our first important result at the conference. And this is this slide, one of the slides we used at the conference. And by the way, you may notice only this page is strange, or these are written by hand. In fact, more than 20 years ago, we didn't have PowerPoint. So we had to copy the data onto a transparent plastic sheet. Then we wrote down several comments, and then we showed this slide using this kind of machine, which was called projector. So, well, I already forgot how to say. Anyway, so 20 years ago, the technologies were quite different. But anyway, there is a reason I show you this slide, because, well, the data shown here were very important. And in particular, the lower panel was very important. Therefore, I want to explain a little bit about the data shown in the lower panel. So, this was the data for muon neutrino events. And the horizontal axis shows the arrival direction. One means neutrinos are coming from above, so they are downgoing neutrinos. -1 means upward-going neutrinos. They came from the other side of the Earth. And of course, 0 means neutrino came from horizon. And these small black circles with error bars show the data, and these hatched squares show the prediction based on simulation. And, well, clearly, for downgoing neutrinos, the data and the simulation agreed quite well. But for upward-going neutrinos coming from the other side of the Earth, the observed number of events was approximately one half of the prediction. And this data can be extremely well explained if neutrinos oscillate when they travel long distance. And therefore, with this data, physicists were convinced that neutrinos oscillate. That means neutrinos have small mass. Okay, well, we presented this data at a conference for physicists. However, something unexpected happened. President Clinton of the United States gave a talk at MIT's commencement on this day, July 5th, 1998. And in this talk, he mentioned about the results from Super Kamiokande. Of course, the whole talk is long. Therefore, here I show you the relevant part to neutrino oscillations. And let me read. Just yesterday in Japan, physicists announced a discovery that tiny neutrinos have mass. Now, they may not mean much to most Americans, but it may change our most fundamental theories, from the nature of the smallest subatomic particles to how the universe itself works, and indeed how it expands. And of course, as the US president, he mentioned that in Super Kamiokande, US people have been contributing. Then he came back. The other issue is that these kinds of findings have implications that are not limited to the laboratory. They affect the whole of society, not only our economy, but our very view of life, our understanding of our relations with others, and our place in time. Sorry, time is missing. Okay, well, certainly it was really an honor to hear this kind of remark by the US president on the next day. Well, really, we were honored. Okay, now I want to move on to the next oscillation discovery. That was the discovery of solar neutrino oscillations. Well, some time ago, people didn't understand how the sun shines, how the sun generates energy. But now people understand that the sun generates energy by nuclear fusion processes. And during these processes, many neutrinos are produced. Therefore, people had an idea, okay, in order to confirm the energy generation mechanism of the sun, we should observe neutrinos from the sun. In fact, the number of neutrinos passing through our hand per second is tremendous. This big number, about 10 to 13 neutrinos per second is passing through our hand. So people wanted to observe solar neutrinos to confirm the energy generation mechanism of the sun. In fact, the first experiment was carried out about 50 years ago. The pioneering Homestake solar neutrino experiment, this experiment, observed solar neutrinos for the first time. And because of this observation, Ray Davis Jr. received the Nobel Prize in Physics in 2002. However, there was a problem. The event rate was only about 1/3 of the prediction. It was a very strange result. There must be something wrong. Therefore, people try to observe solar neutrinos by different methods. However, this problem was only confirmed by the subsequent experiments in the 1980s and 90s. So we knew this problem, called solar neutrino problem, for more than 30 years. But we couldn't understand what was the cause of the problem. And finally, in 2001 and 2002, this problem was understood to be due to neutrino oscillations. And the main detector, main experiment to discover solar neutrino oscillation was this detector. It is called SNO, SNO. It is an, again, underground large neutrino detector, and it used 1,000 tons of heavy water. In fact, heavy water is a very, very expensive material. If you are interested in the price for 1,000 tons of heavy water, you can easily check on the net. Please check. It's really expensive. Anyway, fortunately, the Canadian government had 1,000 tons of heavy water. Therefore, physicists were able to use the heavy water of the Canadian government, and they carry out the experiment. And in fact, with heavy water, the SNO experiment is able to observe the total neutrino flux independent of the neutrino type. Also, the SNO experiment is able to observe the electron neutrino flux only. And then the result is shown here. If the SNO experiment observed electron neutrino flux only, then the event rate was only about 1/3 of the expectation. But if the SNO experiment observed the total neutrino flux independent of the neutrino type, then the observed flux was as expected. And since the sun can only generate electron neutrinos, these two data clearly told us that about 2/3 of the neutrinos coming from the sun are changed or converted to muon neutrino and tau neutrinos. And this was the evidence for solar neutrino oscillations. And because of this result, Art McDonald received the Nobel Prize in Physics in 2015. So that was another discovery of neutrino oscillations. But you may wonder why we are so excited with the small neutrino mass. Well, we know electrons have mass, quarks, which exist inside protons and neutrons, these particles also have mass. Then, in a sense, it's natural that neutrinos have also mass. Then why we are so excited with the neutrino mass? Well, yes, we are excited. And I would like to convince you why we are excited. Here, I show you the mass of particles. Well, there are 3 different particles. They are like electrons, but 3 different types. And these particles mass are shown by red here. And there are 6 types of quarks. And these mass are shown by blue and green colors. Now, after the discovery of neutrino oscillations, the physics community has been working extremely hard to understand the neutrino mass better. And now, we had a fairly good idea about the neutrino mass themselves. And let me show you the neutrino mass and plot here in this. And they are here. So clearly, neutrino mass are plotted in a rather different place in this figure. And I'd like to ask you to be careful about the horizontal axis. Here, 1 unit is 100. If you have 3-unit separation, that means the mass are different by a factor of million. So now you can read, and you immediately notice that the neutrino mass are approximately, or maybe more than, 10 billion times smaller than the corresponding mass of quarks and charged leptons. 10 billion, or 10 orders of magnitude smaller. Clearly, neutrino mass are extremely small. And we think we are unable to explain this kind of extremely small neutrino mass within the framework of the present day standard model of particle physics. So we are excited, and we believe this is the key for us to better understand elementary particles and the universe. Well, certainly, it's very important to understand elementary particles better, to understand these extremely small neutrino mass. But I also mentioned to understand universe better. Why? Well, in fact, we have a big mystery in our universe. Here, I show you a photo of the far universe. You can see many stars and many galaxies. And there's one thing we know for sure. These stars and galaxies are made of matter. We know there's no antimatter star, no antimatter galaxy. Yeah, it seems to be too obvious. By the way, well, according to the physics law, if there is matter, there should be antimatter. For example, we have protons, then there should be antiprotons. Protons have +1 charge, antiprotons have -1 charge, and they have exactly the same mass. Okay, but all these stars and galaxies are made of matter particles. Then you may ask, why we have a problem? Why we have mystery? Well, in fact, we know that our universe began with the Big Bang. And in the Big Bang universe, the temperature was extremely high. And in this Big Bang universe, the matter particle and antimatter particle were always created simultaneously. And therefore, in the Big Bang universe, there must have been equal number of matter particles and the antimatter particles. Then, with the universe cooled down, matter particle and antimatter particle meet and annihilate, disappear. So, if we think naively, there should be no particle, no antiparticle in the present-day universe. But clearly, we exist. We are matter. We are made of matter. So we have to understand why we can exist. In fact, we almost understanding. In the Big Bang very hot universe, the number of matter particles was, I would say, 1 billion 1. On the other hand, number of antimatter particles was 1 billion. They were almost equal. Then, with the cool down of the universe, matter particle and antimatter particle meet and annihilate, disappear. So, now we have this one matter particle, and this is us. So this way, we can explain. Well, but in this explanation, we are cheating. Well, of course, 1 billion one is very close to 1 billion, but not exactly. Therefore, we have to be able to explain why there was extra 1 in the matter side. In fact, we do not understand why there was extra 1 in the matter side. But we are thinking that neutrinos with very small mass might be the key to understand this extra 1 in the early universe. So we have an idea, but this is still an idea. Therefore, we have to check if this idea is correct. And for this, we need to do the experiment. Unfortunately, the present-day experiments are not powerful enough to study this kind of effect. In fact, we'd like to observe if oscillation of neutrinos and those of antineutrinos are different. If we observe the difference between neutrinos, neutrino oscillation, and antineutrinos, neutrino oscillation, then this should be the first step for us to understand the origin of the matter in the universe. As I said, we'd like to observe this effect, but the present-day detectors are not powerful enough. So we need the next-generation neutrino experiment that is hyper-Kamiokande. And in fact, as shown here, we would like to produce the beam of neutrinos by the JPAC accelerator facility, and also anti-neutrino beam is created in this facility. And then we observe oscillation of these neutrinos and antineutrinos in the hyper-Kamiokande detector. So this is our plan, and I want to briefly discuss the hyper-Kamiokande detector. It is another factor of almost 10 increase in the mass. So it's going to be about 68 meters in diameter and 72 meters in height. And it will contain 0.26 megatons of very pure water. And with this detector, in addition to the science described in the previous page, we expect many other important research topics in this detector. And in fact, it is going to be an international collaboration of physicists. And even now, we have about 340 members from 17 countries. And of course, the researchers from India are involved in this experiment. Then you may ask, can this kind of detector be constructed? Can you get the money for this? Well, let me explain the status of the hyper-Kamiokande detector. On August 29th this year, our funding agency has submitted its budget request, including hyper-Kamiokande, to the Ministry of Finance. Then the Japanese newspaper reported this decision of the funding agency very positively. So, well, in fact, we are very happy to know that the Japanese newspaper, that means Japanese people, were rather supporting our next generation research project. Then, on December 13th, the Japanese cabinet has proposed the supplementary budget for this fiscal year, and it includes the budget for the construction of Kamiokande. Also, the proposed regular budget for fiscal year 2020, next year, that was announced on December 20th, includes the budget for Kamiokande. So, the construction of the Kamiokande experiment will start soon, and the experiment itself will begin around 2027. And so this is really a very exciting moment, and we'd like to work together with the Indian and the international colleagues in this kind of dream experiment, Kamiokande. Okay, let me summarize. As discussed today, neutrinos are really special particles. Atmospheric neutrino deficit was observed unexpectedly in proton decay experiments. Subsequently, in 1998, Kamiokande discovered neutrino oscillations, which shows that neutrinos have mass. The discovery of non-zero neutrino mass opened a window to study physics beyond the standard model of particles. Furthermore, neutrinos with small mass might also be the key to understand the fundamental questions of the universe. Therefore, we'd like to continue studies of neutrinos in Kamiokande, and we really hope that we can work together with their Indian colleagues in Kamiokande. Okay, that's all. Thank you very much for your attention.
Thank you, Professor Kajita. Now we have time for some questions. So if you have any question, please come to the aisle here, identify yourself, and then ask your question. So here are my colleagues are standing with mics. So any one of you have questions, please come in the aisle here, either on this side or that side. Okay, go ahead.
Good evening, Professor Kajita. My name is Prasad Pawar. So my question was, if electron neutrino is converting into other types of neutrino, where does the mass come from? Where does the mass come from? If electron neutrino is converting into tau or muon neutrino, where does the extra mass come from?
Thank you very much for this question. In fact, it's not possible for neutrinos while traveling can change their mass. It's not possible. It's conflict with the fundamental physics law. Therefore, the neutrino mass is always constant, but they change their type. Okay?
It's a mystery. That's what he wants to find out. Okay? Here, there is a question by a young person here.
Hello, my name is Yuvan Arya. I had a question that if your first experiment, the Kamiokande, was to find out the decay of protons, why did you estimate the amount of muon neutrinos? Why did you estimate the amount of muon neutrinos and electron neutrinos?
Okay, his question is that if you are looking for
Proton
nucleon decay,
Yeah,
proton
yeah.
decay, why did you have to estimate the number of muon neutrinos and electron
Yeah,
neutrinos?
yes, okay. Well, because in order to search for proton decays, we have to understand the background very carefully. Therefore, we had the number of expected muon neutrino and electron neutrino events.
Thank you. And what is antimatter particles?
What?
He's asking what are antimatter particles?
Oh, antimatter particles. Okay, thank you. Well, okay. It may not be so easy, but anyway, let me try. Well, okay. Our body is made of matter particles. Well, one of them is the proton. Proton is one of the matter particles. And the physics law tells us if there is a matter particle, there should be antimatter particle. And the difference is proton has +1 charge, electric charge, but antiproton should have -1 electric charge. And they have exactly the same mass.
Okay, thank you.
Yeah.
Okay, thank you. Okay, next question over there.
Hello, sir. So my name is Yuvraj, sir. So my question is, we have discussed so much about neutrinos, but I want to ask is what is the basic difference between a muon neutrino and a tau neutrino? Because they are two different entities, they're oscillating between each other. So
Yeah.
what is differentiating between them, sir?
Thank you for this question. This is actually a very important question. Well, okay. The neutrino type is defined this way. If a neutrino interacts with, say, nucleus, and if a muon is produced, then we know that the neutrino was muon neutrino. Instead, a tau lepton is produced, then we know that the neutrino was tau neutrino. And this way, we know the neutrino type.
Hello, sir. I am Anirudh from IIT. I wanted to know that you mentioned that there are solar neutrinos, which are electron neutrinos. So in the universe, there are many stars which might give out electron neutrinos. So in a detector, how do you realize that a certain neutrino, is it from our sun or from some other star?
Okay, thank you. This way, you can understand. Well, certainly, all the stars produce solar neutrinos. That's true. However, other stars are very far away. And therefore, the neutrinos coming from the other stars are very small.
So are we trying to neglect that number in comparison of our solar neutrinos?
Yes, well, it's a very good approximation. You can neglect the contribution from the other stars.
And one more doubt, you showed the diagram of conversion between the different type of neutrinos. Is this oscillation continuous? So are there intermediate types of neutrinos other than the three, or is it a discrete conversion directly from one to another and then back and forth like that?
Say again?
Like you mentioned the oscillation of neutrinos. So in the diagram you showed a continuous sort of variation. So are there intermediate types of neutrinos existing? Do we know anything about them?
Okay, actually very good question, yes. Well, in the diagram, initially a muon neutrino, then at some point tau neutrino, then in the intermediate stage. Well, in the intermediate stage, these neutrinos are partly muon neutrino and partly tau neutrino, and we know the type of the neutrino only if they interact at that point. If they produce produce a muon, then the neutrino was muon neutrino. If they produce a tau particle, then that neutrino was tau neutrino.
Thank you, sir.
Okay, next question.
Hello. Hello. Hi, sir. Sir, I want to ask that what is the basic use of neutrinos?
Oh, use of
Yeah.
neutrino.
Yeah.
Very good question. I have no idea.
Thank you, sir.
Well, they obviously play a very important role in the way universe works. So in that sense, it's important, but maybe no immediate economic benefit.
Right. As far as our daily life is concerned, no relevance.
Okay.
Thank you, sir.
Next.
Hello.
Please identify
Hello,
yourself.
sir. I'm Abdul. So my question is, how is this discovery of neutrinos and the further research going to affect the tech industry, and which sector of tech industry is going to affect the most?
Industry?
Technology.
Yeah, the tech
is it
industry.
Going to affect technology of future? And which area?
I see. So the question is future technology, right?
Yes.
Okay. Okay. Well, first of all, our electronics is quite advanced, and therefore we may have some influence to the very fast electronics. Also, the amount of data we have to store and analyze are also quite big. Therefore, in that sense, we may have some impact to the computing things. And finally, our photodetectors are very special ones, and we need the very high quality photodetectors, and therefore we may have some impact to these industries.
Thank you so much.
Okay, next.
Sir, I am Akash from Jain College. So,
Please put the mic close to you.
Yeah. I am Akash from Jain College.
Ask your question by keeping it close to you. Okay,
So, I think the speed of a neutrino is around 2.8 lakhs kilometer per second, if I'm not wrong.
What is that? Speed of?
The speed of a neutrino would be around 2.8 lakhs per second, if I'm not wrong.
300,000 kilometers, 3 lakh.
Yeah, okay, fine.
Yeah.
So, and you told us that millions of neutrinos travel through our hands per second. So, if a particle has a mass, so there should be, if it moves through the space-time curvature of any mass, so it should show some effect.
Okay.
So the question is, if there is a mass in neutrino, then there must be some effect in the propagation.
Yeah, it travels around the particle which has a mass, or the bigger mass. So because it has a bigger mass, so there would be the bending in the space-time curvature. So my question is there no effect to the neutrinos? So neutrinos have no effect for the space-time curvature, bending of space-time curvature.
Okay, so these are two different things. So I think what he's asking, that if neutrinos have mass and they're traveling through space and so on, it should have some effect. So why there is no effect? Why neutrinos are not affecting when they're going through our hand? It's not making any difference.
Yeah, okay. In fact, the neutrino mass has some effect in the formation of the structure in the universe. Compared with the, say, no mass case, the structure of the universe should be slightly different because the neutrino travels slightly lower with lower speed. However, the effect is very small. And in fact, people would like to observe the effect of the neutrino mass by studying the structure of the universe very carefully. But unfortunately, as of now, there's no convincing evidence for the neutrino mass from the studies of the structures in the universe yet. But maybe in the near future, we will have in fact, the effect of the neutrino mass in the structure of the universe.
So if I may add to what Professor Kajita said, neutrinos have effect on large-scale structure of universe. It doesn't affect your hand. It has no effect on the hand, but it may have effect on the large-scale structure of the universe. So it's interesting.
That only I asked means,
yes.
If it travels around the Earth, so there is bending of space-time curvature. So
well, that is based on present understanding.
Yeah.
So let's move on. I think we have any other question?
Sir, I am Path Manzrekar from Atomic Energy Central School 1. I have a doubt.
He's there.
I have a doubt. What is the specialty of water that makes it able to track or trap neutrions?
So he's asking why in water you are able to track the neutrino interactions.
Oh, thank you. Why we are able to observe the neutrino interactions in water? Is it correct?
Yes.
Okay. Well, if a neutrino interacts with a nucleus in the water, then a charged particle is emitted, and this particle emits light. So we are able to observe these light by photodetectors.
Thank you, sir.
Okay, is it here? Yeah, please identify yourself.
Sir, I am Nishan Patil from AEJC. Sir, what is the mass of neutrinos?
What is the mass of the neutrino? Oh, in gram.
Yes, sir, means how many grams?
Oh, I should know, but
10 raised to minus 10.
Well, 1 gram contains 10 to 23 protons, 6 times 10 to 23, and the electron mass is only
2,000 times smaller.
2,000 times smaller. Then the neutrino mass is 5 orders of magnitude smaller.
Okay, so 10 raised to minus 33 or 34. Very, very small. 1 followed by 34 zeros in the denominator. Grams. Okay, next.
Sir, what is the difference between muon neutrino and tau neutrino?
Difference between muon neutrino and tau neutrino. Okay, yes. We can only know the neutrino type, muon neutrino or tau neutrino, after they interact with the matter. If after the neutrino interaction, a muon is produced, then the neutrino is muon neutrino. Instead, if a tau particle is produced, then the neutrino was tau neutrino. This is the only difference.
Okay, is there any other question? Okay.
What is lifespan of neutrino?
Can you speak in the mic?
Lifespan of neutrino.
She's asking what is the lifetime of neutrinos?
Lifetime of neutrino. Well, okay, we do not know. But there's, as far as we know, there is no reason for neutrinos to decay to other particles. Therefore, in this sense, neutrino life should be almost infinity.
Thank you.
Okay.
Sir?
Yeah, go ahead, please.
Hi, I just wanted to ask, what are the other scientific fields that are getting impacted by neutrinos?
Scientific what?
What are the other scientific fields that are getting impacted by neutrinos?
Asking what are the other scientific fields which are getting affected by neutrinos?
I see. Okay, yes. Since neutrinos have mass, and well, this part I didn't explain. Since neutrinos have zero charge, and well, also I discussed today, if there is a matter particle, there should be antimatter particle. And if matter particle has +1 charge, antimatter particle should have -1 charge. However, neutrinos have zero charge. Therefore, we are not sure if neutrinos and antineutrinos are really different particles. And this should be checked. And in order to check this, we have to study a special decay of a nucleus, special nucleus. And therefore, neutrino physics is related to the nuclear physics nowadays. Is it okay?
I think that's close enough. Okay, I think there's one over there.
Hello, sir. I'm Ananya from AJC. I had a question. If neutrinos don't have any charge, then how are they converting into muononeutrinos and tau neutrinos? And how are they emitting mu and tau?
Okay, yes. Yes, that's right. Neutrinos have zero charge, but if a neutrino interacts with a nucleon, for example, then muon or tau is produced, and they have charge. Okay, well, to explain this, well, it's not so easy. This is actually a feature of the neutrino interaction. Surprisingly, these neutrinos, if they interact, they change their charge. But
You
of
said
course,
they don't have any charge.
they don't have charge, but after the interaction, the produced particle has a charge.
Yeah.
Okay.
I'm Dilkhush from Jai Hind College, and I have two questions. Why are neutrino detectors based underground?
Yes, okay, thank you. Neutrinos are very difficult to observe. And even, for example, even super Kamiokande, we observe only 10 events per day, 10 neutrino interactions per day. But we have many background events. And background events are cosmic ray particles. And in order to avoid these cosmic ray particles, we go deep underground. If we go deep underground, the number of cosmic ray particles are very much reduced.
And one more question, do neutrinos decay?
Neutrinos decay? Okay. Well, of course, we cannot exclude the possibility of neutrino decay. But as far as I can imagine, neutrinos are essentially the lightest particle. Therefore, they cannot decay to other particles. So I think neutrinos do not decay.
Any other question? Okay, please.
Yeah, I have a very different kind of question. What is the time scale for Kamiokande? What's the time scale?
Scale for the construction or?
Yeah, construction and experiment, or maybe
yes.
the time scale for the next
yes.
Nobel Prize.
The construction will be 7 to 8 years, and the experiment will continue at least for 20 years. Well, 20 years is actually a very short time. We have been operating Super Kamiokande for more than 20 years.
Okay, thank you.
Oh, there is one more question this side.
Hello sir, my name is Namrata Koende from AEJC. My question is, how can we catch neutrinos in beta decay reactions?
Neutrinos?
She's asking in beta decays, the neutrinos that are produced in beta decays, how do you detect them?
Oh, neutrinos produced by beta decays. I see.
Radioactive decay.
Okay. Well, of course, in order to observe these neutrinos, we have to produce many neutrinos because most of the neutrinos simply pass through even the Earth. Then the question is, how can we produce such many neutrinos around us? And as far as I can tell, the easiest place is the nuclear power stations. There are many, many beta decays occurring inside the nuclear power station. Therefore, if we have a detector nearby, we can rather easily detect these beta decay neutrinos.
Okay, sir, one more question.
The first neutrino was detected, right?
Yes, that's right, yeah.
Sir, one more question. It was also said that the neutrinos can also explain the mystery of universe, that how it expands. So how, sir?
Yes, thank you. The President Clinton meant was, I believe, depending on the mass of the neutrinos, the expansion speed could be different. That was meant by President Clinton. But now we know other factor could be even more important than the neutrino mass.
Thank you, sir.
Good evening, Professor. My name is Ruchir. My question is, I understood at one time in the presentation, it said that neutrinos oscillate, and that proved that there was a mass to the neutrino. The question is, why does oscillation prove that there is mass? And why does matter oscillate, if that's a property of matter?
Yeah, okay. Well, let me, to the first question, let me explain this way. If neutrinos change their type, whatever the way, mechanism, that means neutrinos have mass. Because, well, we know the Einstein theory of relativity, special relativity. And according to this, if the particle's speed is getting higher and higher, then the clock of this particle gets slowed down. And finally, if the particle propagates with the speed of light, then the clock stops. Now, if neutrinos change type, that means the neutrino clock is not stopping, because the changing type means you need time. So if neutrinos change type, definitely neutrinos should have mass. And then the second question I forgot.
Second, why does matter oscillate?
Oh, why matter? Okay. Yeah. Okay. Why neutrinos oscillate? It's a bit more complicated thing. I have to really tell you the mechanism. And in fact, well, a neutrino is actually a combination of the essentially three mass eigenstate of the neutrino mass state. And these three mass eigenstates propagate coherently in space. But depending on the mass of the mass eigenstate, the internal clock's clock speed is slightly different. Therefore, after some time, the neutrino type cannot be identical as the original neutrino type. And if you calculate, then you find out that, in fact, neutrino type is changing.
Good evening, sir. I am Purnima from ACS 4. My question is, what inspired you to work on neutrinos and not on any other particles?
What inspired me?
To work on neutrino physics and not in any other area of physics.
Well, okay. Well, to me, any other research is also quite important, quite inspiring. I simply, accidentally, involved in neutrino physics.
Hello, sir. My name is Anas from Badlapur. Sir, here.
Oh, yeah.
My question is there any relation between electrons and neutrinos?
Electrons and muons. Relation between electrons and muons. Oh, it's a very fundamental question. Well, to be honest, I don't know, and I think most of the physicists, or all of the physicists, do not know the fundamental relation between electrons and muons and tau leptons. It's a very fundamental question. We do not know yet.
Thank you, sir.
We only know that they are different. Okay. I think one last question. Okay. Then we'll close the
if you have, say, enough density of mass to actually stop neutrinos or reduce their speed down by, say, multiple reflections and letting it lose a lot of momentum, could you treat neutrinos as some kind of condensed matter or do experiments with it eventually or hypothetically?
Thank you for this question. In fact, this kind of situation occurs or should be occurring inside the supernova explosion. And well, during the supernova explosion, for about 10 seconds, the very high density star exists inside, at the center of the supernova. And because of the densities, because of the extremely high density, neutrinos cannot easily propagate. And in fact, because of the extremely high neutrino density inside the supernova core, and the feature of the neutrinos, for example, neutrino oscillation, is expected to be quite different. But this is an extremely difficult question, and people are still trying to understand what's going on inside the core of the supernova.
Okay, I think we'll conclude today's discussion.
Yeah.
Thank you very much, Professor Kajita.
Thank you.
And thank you all of you.